in the order of names that appear on this box. I'll remind you after Jim's lecture about how to proceed. Jim, without further ado, the floor is yours.
Thank you very much, Edward. It's a pleasure to be here. This is a talk on the direction of causation, or the direction of explanation. And I should say, by way of background, is that I gave an early version of this talk some years ago at a conference, which was, I think, the 50th anniversary of Hempel's Aspects of Scientific Explanation. And that's why the reference to flagpoles is in the talk. Since then, the paper, the talk has been turned into a paper. As is my wont, the paper has been greatly expanded. There is now a version of it on the PhilSci archive, and through the good offices of John Norton, a version of the paper is going to appear in the online journal Theoria sometime fairly soon. Okay, so here's what I'm going to be talking about. I need to move something out of the way here. Okay. This is the plan for the talk. I'm going to explore some themes having to do with the direction of causation or explanation. I'm using the Hempel flagpole example as motivating. And I'm also going to draw on some ideas from Eugene Wigner's collection of essays, Symmetries, and Reflections. I'm going to interpret these as some of the ideas in this essay as describing a certain kind of ideal of explanation, or causal analysis, as I'm going to call it. The ideal is certainly not satisfied everywhere or in all areas of science, but when it is satisfied, I think it gives us some machinery for thinking about causal direction. The ideal itself involves two different strands, an idea about the desirability of finding initial conditions that are independent of one another in a certain kind of way, and then in addition to that, the satisfaction of a further independence condition, which has to do with the relationship between the laws governing the system, or the causal relations that characterize the system. Whoop. Okay. I'm going to also try to show you that broadly similar ideas have been used in recent work from machine learning literature in inferring causal direction. So there's a kind of interesting connection here between ideas that are more philosophical and ideas that are actually turn out to be practically useful for inferring causal direction. And then I'm going to try to show you how these ideas taken together can help with us understanding what's going on in the flagpole example. Here are some of the machine learning papers that I found useful in thinking about these problems. If you're interested in questions of this sort, I recommend them to you. They're really, I think, not just practically interesting, but they're philosophically also very interesting. Also, I did want to mention some connections to previous philosophical ideas, particularly ideas from David Papineau and Dan Hausman, which both of these writers have highlighted the significance of independence assumptions among the causes of an effect in leading to inference about causal direction. And there are also some connections to ideas of Kevin Hoover. Hoover, some of you may know, is a philosopher and also an economist, and he's done interesting work in macroeconomic contexts on problems having to do with inferring causal direction. So I'm going to begin with an interventionist account of causation. I'm not going to say much to try to defend this here. I'm going to assume that this is at least a little bit familiar, maybe to some of you. So the idea is that X causes Y if there's a possible intervention on X, such that if that intervention were to occur, the value of Y would change. You can think of this as broadly the same thing as what's captured by Judah Pearl's do operator. Think of an intervention as something like a unconfounded experimental manipulation of X for the purposes of understanding whether X causes Y. Okay, so here's the flagpole problem, just to remind you. From the height h of the pole, the angle theta that the sun makes with the Earth's surface, and laws about the rectilinear propagation of light, one can deduce the length of the shadow cast by the pole, and intuitively this strikes us as an explanation of the length of the shadow. We think of the angle theta and the height of the pole as causes of the length of the shadow. But of course, you can run the derivation in the other direction. You can deduce the height of the pole from the length of the shadow and the value of theta and the same law as L, but that doesn't strike us as an explanation, and it seems, that derivation seems to, as it were, get the causal direction wrong. We think that it's H and theta that cause S rather than S and theta causing L. So it's just that fact that I'm going to be, this apparent asymmetry that I'm going to be trying to understand in the course of this paper. Now, there are various ways of responding to the observation that there's an apparent asymmetry here. One response, and I take this to be the response of Hempel himself, and maybe in a somewhat different way, it's von Frassen's response too, is to say that the difference between the two derivations is quote unquote merely pragmatic. We may find, for whatever reasons, that the derivation in one direction is somehow more psychologically satisfying, more relevant to our interests, but this doesn't reflect any objective difference in explanatory goodness between the two derivations. There really aren't, it isn't as though, as Hempel and others like Van Fraassen have claimed, it isn't as though you're sort of objectively getting some directional feature wrong. So that's one possible response. I'm going to defend the idea that there really are objective differences between the two putative explanations that are relevant to their goodness qua explanations. In other words, the difference between the two derivations and the difference between an inference from cause to effect and from effect to cause, I'm going to claim, is not merely pragmatic, whatever merely pragmatic means. Now, here's another aspect of the whole discussion that is worth just a brief mention. What about the role of time order in all of this? You might think that the problem of identifying the causal or explanatory direction is an easy one. You might say, look, given two correlated kinds of events, C and E, the cause is just the one that occurs first temporally. C causes E if C temporally precedes E. This is, I think, unsatisfying for a number of different reasons, as I hope my discussion below will show, but one primary reason why it's unsatisfying is that we seem able to identify causal direction even in the absence of temporal information. There are lots of realistic cases in which we have patterns of correlation among variables, and for one reason or another, we don't know what the time order is, but nonetheless, we seem able to reliably infer the causal direction. So I'm not going to take time order to be the crucial consideration here. Now let me turn to a couple of some brief remarks about Wigner and his collection of essays, Symmetries and Reflections. One of the themes that runs through a lot of the essays in this collection is the idea that in science we somehow make a cut or a distinction of some kind between initial conditions and laws. We allocate some features of the systems that we're trying to analyze to facts having to do with initial conditions. Other features have to do with the laws or generalizations governing the system. Wigner thinks that finding the right way of making this cut is a very, very crucial step in scientific theorizing. So suppose we do succeed in making the cut. What are the characteristic features of the two components, the initial conditions and the laws or governing generalizations? Well, this is what Wigner says. He assumes that the laws should have various kinds of invariance properties. He particularly mentions the role of symmetries like spatial translation invariance and so on and so forth in characterizing laws. But I think it's not reading too much into what he says to suppose that he's also assuming that the laws should have a more general kind of invariance property. That is, they should be stable or they should continue to hold as the initial conditions vary, at least for some range of variation in initial conditions. So you can take Newton's laws of motion and his inverse square law of gravity, and you can combine these with a whole variety of different initial conditions to describe, for example, trajectories of planets, motions of projectiles near the surface of the Earth, and so on and so forth. And the idea is that the laws are going to continue to hold. They're going to, as it were, remain stable or invariant as you change the initial conditions. We don't expect the initial conditions to have similar sorts of invariance properties. So this is what I'm going to mean by invariance. You have a relationship linking x to y, and it's going to be invariant if it remains stable or continues to hold under interventions on x, and typically under other sorts of changes as well. And you should be able to see that there's a close connection between this and what I said earlier about interventions, because if intervening on x is going to be a way of changing y, then there has to be some degree of invariance in the x to y relationship. Now, here's another way of putting the idea that I just described about invariance, and it's the following. What we're expecting or demanding is that the laws or the governing generalizations should exhibit a certain kind of independence from the initial conditions. Now, what does independence mean here? It obviously can't mean probabilistic independence. The laws are not random variables, for example. So how else might we understand the notion of independence? In the machine learning literature, in which something like this idea is appealed to, as we'll see, a lot of the research understands the relevant independence conditions in terms of a certain kind of informational independence between the laws and the initial conditions. Roughly, the idea is that there shouldn't be, as it were, non-generic relations or constraints between the laws and the initial conditions. The laws shouldn't tell you anything specific about what the initial conditions governing a particular system are, and vice versa. And this, of course, is very closely connected to the idea that the initial conditions should be, as it were, sort of freely combinable with the laws, and the same law should be combinable with many different initial conditions. So here's a statement of the same idea. If you want a metaphor, you might think of this in terms of the idea that nature or God chooses the laws and the initial conditions independently of one another. So that's one kind of independent condition. Here's another one. It has to do with independence conditions that Wigner thinks should apply to the initial conditions themselves. He says these should be as random as the externally imposed gross constraints will allow. And he says that the existence of regularities in initial conditions should be considered unsatisfactory. Now, I think what he means here is, of course, there are often regularities in initial conditions, but there's some sort of thought here that to the extent there are such regularities, they should be traceable back to initial conditions where there's some kind of randomness or statistical independence present. And I just want to flag the idea that this suggestion about initial conditions and randomness in initial conditions is closely connected to a familiar philosophical idea, the so-called principle of the common cause, where this says if X doesn't cause Y and Y doesn't cause X, and they have no common cause Z, then we assume that X and Y are statistically independent. So in other words, the thought is if there's no causal relationship between X and Y, then where causal relationship means no common cause and no direct causal connection, then it's at least a kind of default assumption that they're going to be statistically independent. If we find that they are dependent, then this is a clue that some relevant causal fact has been left out of the model. This is connected to ideas about the independence of incoming influences and so on that you sometimes see discussed in the physics literature. So if you put these two ideas together, you get a kind of ideal of explanation or causal analysis. We explain by separating the description of systems into two components, a set of generalizations or laws, and a set of initial conditions. And we want the laws or generalizations to be invariant, at least to some substantial degree, over changes in the initial conditions. And we then explain the behavior of a system by exhibiting how the behavior depends on the generalizations and the initial conditions taken together. And furthermore, we want to impose the constraint that the initial conditions should be, as far as possible, independent of one another. Now, I'm certainly not claiming that all explanations in science or all theories in science embody this kind of ideal. In fact, it's easy to think of cases in which this is not so. But I think this picture sometimes does apply. And when it does, my claim is that we can use it to get a purchase on causal or explanatory direction. Now, as I'm also going to try to illustrate, you can think of these independence ideas in another way, which is associated with what I just said, and that is in terms of a desire to avoid gratuitous coincidences or certain kinds of fine-tuning. Coincidences either in the sense of dependencies among the initial conditions themselves, or coincidences in the sense of the laws and the initial conditions being specifically tuned to one another. And I'll give you some illustrations of what that might involve shortly. So these two ideas are going to be the basic building blocks that I'm going to appeal to in my treatment of causal and explanatory asymmetry. And again, just to remind you of what I take the problem to be, the issue of finding the direction of explanation or characterizing the direction of causation is the issue of identifying what information, if any, provided by a cause or a candidate explanans, in virtue of which it's appropriate to think of the explanation or the causal inference going in one direction and not in the other direction. That's the puzzle I'm going to be trying to make some progress with. What is it about the flagpole example that leads us to think that the length and angle to length of shadow derivation is the correct or explanatory one? So I'm going to just give these conditions to which I appealed a little while ago some names, call them variable independence and relationship independence. Variable independence is the idea that we have some sort of expectation that cause variables or variables that characterize initial conditions should be independent in something like the sense of statistical independence. So this is a version of Wigner's assumptions about random initial conditions, or at least we expect this to be true insofar as there's no further causal relationship either among the initial conditions themselves or a common cause of the initial conditions. So the second idea I'm going to call, which I also talked about, I'm going to call this relationship independence. And this has to do with the independence of the causal or explanatory relationship between two or more variables. So what we're going to ask here is whether the relationship between X and Y is independent of the either the value taken by the independent variable X, or in some cases, we're going to ask whether it's independent of the probability distribution of the independent variable X. And this is, as I said earlier, this is what I take to be an idea of invariance. Okay, so now let me say a little bit more, first of all, about variable independence. So what I'm going to be assuming is something like, or arguing for is something like this. So variable independence involves the idea that when a relationship involves 3 or more measured variables, say X, Y, and Z, or to take another possibility, 2 variables that are measured, X and Y, and an unmeasured noise or error term, and 2 of the variables are independent, but no other pairs are independent, then it's often reasonable to infer that the correct causal direction is from the independent pair to the 3rd variable. So I'm going to use this symbol here, which is frequently used in the statistics literature for independence. The first claim here is that X and Y are independent of one another. We write this in the way indicated. I'm going to use the same symbol with a slash through it to mean dependence. So what I'm claiming is that if X and Y are independent, but X and Z are dependent and Y and Z are dependent, then a pretty good heuristic is to infer that X and Y are causes of Z. So in other words, it's the independent guys that are the causes, or the explanatory direction runs from the independent variables to the 3rd variable on which they are dependent. And just to be a little bit more explicit about what I mean by relationship independence, suppose we have 2 hypotheses about causal direction. Suppose they're represented by functions. There's a function from X to Y, and there's a function from Y to X. The function from X to Y represents that X causes Y. Then we're going to ask the question of whether the function f itself is independent of its presumed input X, and we'll ask a similar question about G and Y. And the suggestion that I'm going to be trying to defend is that if independence holds in one of these directions, but not in the other, then the direction in which independence holds is the correct causal direction. And it turns out, rather remarkably, that in the kind of case that I just described, if we impose even relatively weak restrictions on the functions f and g and on the distributions of the variables involved, asymmetries of independence are going to be present just as a matter of mathematics under a fairly wide range of realistic conditions. So we'll find, for example, that at least in many cases, if relationship dependence holds in one direction, it's not going to hold in the opposite direction. And this is one of the things that warrants taking the direction of it in which independence holds to be the correct causal direction. So that's going to be the basic strategy. We're going to be looking at possible asymmetries in independence relations, both variable and relationship independence. And we're going to be using these as cues to causal and explanatory directions. Now, one way of thinking about the upshot of the discussion that I'm going to give you details in a minute, but one way of thinking about the upshot is that there's a lot more content or structure present in many explanations and causal claims that's focused on, that is captured by a simple focus on deductive relationships. Relationships that might look completely symmetrical, such as the relationship between the height of the flagpole and the length of its shadow, when we just focus on deductive relations, can be shown to embody asymmetries, highly relevant asymmetries, when one attends to independence relationships. Okay, so now let me tell you about a couple of results in the machine learning literature. Let's consider a case in which we have 2 random variables, X and Y. They're statistically dependent. They're dependent in probability, but the relationship between them is stochastic or noisy. An error term or a noise term is also present. And the problem is this: we can't observe the error term. We can just observe the probability distribution of X and Y, and we want to figure out whether X causes Y or Y causes X. We're going to assume that no unmeasured common causes are present. And we also assume that the noise terms enters into these relationships in an additive way. So there are just two possible hypotheses about causal direction. Either y is caused by x, which we represent by 1 here, y equals f of x plus u, or it goes in the other direction with a different air term, u prime. Now, to make progress with this, we have to make some assumptions about the form of the functions or the distribution of the variables that are involved. So think first about a case in which the functions f and g are linear, but we assume that the processes that generate the candidate cause variable and the error term are non-Gaussian, that is, they aren't normally distributed. More precisely, actually, for the result, all that you need is at most one of the variables is distributed according to a Gaussian distribution. You can then proceed as follows. So this is what's done in the machine learning literature. You can use a technique called independent component analysis to separate the non-Gaussian distributions into statistically independent components. Then you see whether it's possible to fit an equation of the form 1 here with x and u, the error term, independent of one another. And then you look and see whether it's possible to fit an equation going in the opposite direction with x as a function of y with an error term u and a y and u independent of one another. And if the error term can be made independent of the candidate independent or cause variable in one direction, but not in the other, and then you infer that the direction in which there's independence is the correct causal direction. You can also do this for nonlinear cases. Again, you make the same kinds of assumptions, some of the same kinds of assumptions, no unmeasured common causes, relationship between x and y it involves a noise term which enters additively. Again, you have just these two alternative hypotheses, but you now allow f and g to be nonlinear. Then you can show that if you can fit a model in one direction, which the error is independent, then usually, with certain exceptions, there's no additive error model in the opposite direction. And again, the direction in which there's independence is taken to be the correct model. Just to make a quick remark about this, there's a sort of irony here because as some of you may know, certainly in a lot of statistical and social science applications of causal modeling techniques, until fairly recently, there was an assumption that was frequently made that everything was, all the variables were distributed normally, or they were all distributed in the Gaussian, bivariate Gaussian, et cetera, et cetera. It turns out that the problems of causal inference, or at least problems of inferring causal direction, are harder if you assume everything is Gaussian. In a certain respect, they become easier if you have some distributions in there that are non-Gaussian. And it should be easy to see what the underlying intuition is here. Gaussian, bivariate Gaussian, et cetera, distributions are highly symmetric. You can actually characterize such distributions with very little information. So if you have a Gaussian distribution of a variable, all you need is the mean and the variance, and that characterizes the distribution completely. So there's relatively little information in the distribution, in a sense. If the distribution is not non-Gaussian, then there's more information in the distribution. The distribution is going to be asymmetric in a certain kind of way, and you can leverage that additional information to make inferences about causal direction, and that's basically what these techniques involve. Now, these procedures that I've just been describing have actually been subjected to empirical tests. This is a kind of interesting development here, and it's something that philosophers who think about causation and causal reasoning, they might make more use of tests of this sort. So basically what the researchers who developed these ideas did was that they took cases in which it was thought that we know the causal direction on independent grounds, and then they apply, and you have data about cases of causal direction, which you think you know what the correct direction is on independent grounds, and then you take the techniques and you apply them to the data, and you see to what extent they are well calibrated, to what extent they seem to return the correct decisions. And it turns out that the techniques work reasonably well. They're not perfect, but they're far better than chance. They tend to get the correct result depending upon the details of the data set you're using, in something like 75 or 80% of the time. So why do the techniques work to the extent that they do? Well, I think there are several ways of describing the underlying rationale or justification. And I think you can think of them as drawing on the same set of ideas, but expressed slightly differently. First, you might think about what's going on along interventionist lines, associate the difference between X causes Y and Y causes X with the idea that under the first possibility, but not under the second, we should expect that there are possible interventions on X that will change Y. And assuming that these are the only two possibilities, we're assuming that there are no possible interventions on Y that will change X. Now, suppose we can find, as in the techniques that I was describing a moment ago, an error term U, which is statistically independent of X and which is associated with Y. If we can do this, this suggests, even if it perhaps doesn't conclusively establish, that there's a way of intervening on Y, that is by using U, and setting it to arbitrary values without changing X, because U and X are independent of one another. That's diagnostic of the absence of a causal relationship from Y to X. We change Y and X doesn't change. In addition, the absence of such an independent error in the other direction, the Y to X direction, suggests that there's no factor that's independent of Y that might be used to intervene on X, even though if the correct causal direction is from Y to X, it's natural, at least in many contexts, to expect that such a factor exists. An alternative way of thinking about this, which I think it's really just the same intuition, slightly differently expressed, is we can reason as follows. Suppose that when we try to fit a model of the form 2 here with Y causing X, we find that the error term U star is correlated with Y. We then have a model in which there's an unexplained or accidental dependence between allegedly exogenous variables. So in other words, we have a dependence here between Y and U star, and there's nothing in the model that tells us why we should expect that dependence. If, by contrast, when we try to fit a model in the other direction, we find that we have an error term that is independent of the independent variable. There's no unexplained coincidence between the apparently exogenous variables, so we prefer this model. Okay, so that's my attempt to capture at least some of the intuitions that underlie what these machine learning techniques and why I think they work to the extent that they do. Now, let me try to now apply these kinds of considerations to the flagpole example. So consider first a derivation running from theta, the angle that the sun makes with the surface of the earth, and the height of the pole to the length of the shadow. And let's focus first on a case in which there's just a single pole of fixed height. then variations in theta are going to be correlated with changes in the length of the shadow. Just the natural variation in theta that occurs as the sun goes in its arc across the sky will lead to variations in theta. And we will find S changing, but of course H doesn't change because we're assuming that the flagpole has a fixed height. And so there will be independence between theta and H. So in this direction, explaining S in terms of theta and H, the factors cited in the explanations are independent. On the other hand, in connection with the derivation running in the opposite direction from S and theta to H, S and theta will be dependent on one another. What we will see is that S and theta sort of magically change just in concert with one another so as to preserve exactly the same value for the height H. That kind of failure of independence, or that kind of coincidence in the value of S and theta, is an indication that if we're trying to explain H in terms of S and theta, we've got the causal direction wrong. And of course, this is connected to an asymmetry and manipulability relations. You can manipulate S without changing H. For example, by changing theta, you can take the pole and change its angle with the ground, but one can't manipulate H by changing S. Let me just add as an aside that if you're worried that there's no correlation between H and S, we can fix that by just considering a population of poles of different heights. But it's still going to be the case that in any non-arbitrary population of this sort, H and theta are going to be independent of one another. One can also understand what's going on in this example in terms of unexplained coincidences or dependence relations that are present when one gets the direction of explanation wrong. In particular, if you alter the value of theta, you're going to observe, as I said earlier, corresponding changes in the value of S that occur in such a way that H remains constant. Each variable theta, the values of the variables theta and S are going to change in such a way that they maintain exactly the same value from H. And I take this to be a clue that if we try to explain H in terms of S and theta, we've gotten the direction wrong. So in other words, if we think that the causal direction between S and theta, the causal direction is from S and theta to H, we're in effect assuming something like the causal structure in the diagram here. And in this diagram, there's an unexplained correlation between S and theta, and that's an indication that we've got something wrong. If we get the causal direction right, H and theta explaining S, then there's no unexplained correlation or dependency relation. How am I doing for time here? Anyone?
Yeah, so it's 12:50. You started about 40 minutes ago, so you probably have 15. We can go a bit longer. 15,
okay. So I have enough to
yes.
To finish up here. So let me now turn to the second theme that I identified in Wigner, and this is the idea that there should be an independence relation between the initial conditions and the lawful relationships or generalizations generated in the characterizing the behavior of the system. If we think about this in cause and effect terms, we might think of it in something like the following way. When C causes E, the mechanism or conditions that generate values of C should be independent of and distinct from whatever mechanism is involved in generating E from C. So again, this is metaphorically the idea that it should make sense to think in terms of nature, choosing a distribution of values for the cause variable that are independent of whatever generating function relates C to E. And as I said earlier, this is understood in the machine learning literature in terms of the presence of a certain kind of information independence between the distribution of C and whatever relationship connects C to E. This is kind of metaphorical. Making it precise requires a specification of what's meant by information and informational independence. You can't do this in terms of the usual Shannon-Weaver understanding of information, because there you're assuming basically a notion of information that is linked to statistical independence or statistical dependence. And as we said earlier, the relationship between the governing generalization linking C to E and the distribution of C, whether or not that's independent or not, the independence in question can't mean statistical independence. So the way in which the machine learning literature tries to understand this is in terms of algorithmic information theory. I won't go into the details of that, but in terms of a development within, in terms of making use of the algorithmic information theory, Kolmogorov, complexity and information, etc., you can often produce results showing that when you get informational independence between the C to E relation and the distribution of C in one direction, then you're going to get a failure of informational dependence in the other. Now, I said earlier that the machine learning literature understands this in terms of algorithmic information theory. Unfortunately, as some of you probably know, algorithmic information and ideas linked to it are not computable. So to actually take these ideas about informational independence and apply them to actual examples, you need to make some much more specific assumptions. You need to think in terms of a much more specific context. And here's one illustrative example of how this might be done. Suppose we have two variables that are real valued, x and y, linked by a function f. The function is bijective. The function itself is differentiable, and its inverse is also differentiable. And suppose that the log of the derivative of f and the probability density of x are independent in the sense that I've described here. Obviously, this is a sort of metaphorical notion of independence. Then you can show, just as a matter of mathematics, that the inverse function, the log of the derivative of the inverse function and the probability distribution of y are going to be positively correlated. So in other words, if you get independence of the relationship and the probability distribution of the candidate independent variable in one direction, where independence is understood in the way just described here, then you're not going to get independence in the other direction unless the function in question is the identity. So this suggests a test for directionality, causal directionality, that consists of looking for dependencies between the derivative of f and the density of the candidate cause variable. So you look at the relationship between the derivative of f and the probability distribution of x and the derivative of the inverse function of f and the probability distribution of y. And if you have independence in one direction and not in the other, then you take the direction in which there's independence to be the correct causal direction. So here's an example that I've taken from one of the machine learning papers in question that tries to give you a sense for the underlying intuition. So suppose that we've got x here, which is distributed in a relatively uniform way. This is the probability distribution of x along the x-axis, and this is the probability distribution of y along the y-axis, and this is the function linking x to y. And as you can see, the probability distribution of x, because it's relatively uniform, is not correlated with changes in the slope of the function that links x and y. But if you look at the inverse function going from y to x, you'll see that there are correlations in the slope of the inverse function and the probability distribution of y. And the suggestion is that in this kind of case, the claim that the causal direction goes from x to y is more plausible than the claim that the causal direction goes from y to x. So in other words, we have here a situation, thinking in terms of the diagram, the regions in which f has small slope are going to transform different values of x into regions with very similar values of y. So that what's going to happen is that the density of y is going to pile up around those values. And this is going to mean that there's an informational dependence between the inverse function and the probability distribution of y, while there's independence in the other direction. And again, this is something that can be tested empirically. This describes the result of one particular test where the data in question concerned the relationship between temperature and rainfall on the one hand and altitude on the other. We certainly have the intuition that altitude causes temperature rather than vice versa. Indeed, it turns out when it's applied to this kind of data, you get not perfect accuracy, but accuracy that's very, very well above chance. So here's another example that maybe makes it a little bit clearer just what it is that's going on when we think in terms of these relationship independence kinds of considerations. So remember the causal Markov condition, which is widely assumed in discussions of causal modeling. You've got a graph, a directed graph, the probability distribution over the vertices of the graph, and the causal Markov condition says that every variable is independent of every other variable in the graph, except possibly for the descendants of the original variable, conditional on the parents of the original variable. So in other words, the probability of an arbitrary variable xi is going to be independent of everything that isn't a descendant of xi, conditional on the parents of xi. Now, this condition, the causal Markov condition, is provably equivalent to the following factorization condition. You just take the joint distribution and you write it as this product here, probability of xi conditional on the parents of xi. So for example, in a structure in which x is a common cause of z and y, then the causal Markov condition tells you that the probability distribution will factorize in the way that I've indicated here, assuming again that the causal Markov condition is satisfied for the system in question. So here's a way of applying the value independence assumption to this example. When you have a joint distribution, of course, you can factorize it in many, many different ways. And one way of thinking about the value and relationship independence constraints is that they tell you you should prefer that factorization in which each term in the factorization is independent of the other terms in the factorization, where independence can either be understood in terms of algorithmic independence or perhaps in some other way. For example, in terms of the idea that you can change one of the terms in the factorization without changing any of the other terms in the factorization. And just to illustrate what this means, think of a really simple example in which we have just two correlated variables, x and y, and we're going to assume no common causes. The only possibilities are that x causes y or y causes x. There are, of course, two possible factorizations, which I've indicated here. And the intuition is that the correct factorization, the one that correctly captures the causal direction and the causal structure, is the one for which the terms in the factorization are independent, either informationally independent or they can be changed independently of one another. So for example, if the causal direction is from x to y, then what this implies is that the mechanism or generating process for x, represent this by the probability distribution of x, is going to be independent of the mechanism represented by the conditional probability of y given x, linking x to y. So this then is the appropriate factorization here. So in other words, the thought is that this is the appropriate factorization or the correct causal structure, then you can change the probability distribution of x without changing the conditional probability of y given x. And similarly, you can change the conditional probability without changing the unconditional probability of x. If that doesn't hold, then this is not the correct factorization. So the thought is that, again, that remember what we mean by x, the x to y relationship being independent of the probability distribution of x. What this means is that we expect this conditional probability distribution to remain stable or constant or invariant under changes in the probability distribution of x. If we find this pattern of invariance in one direction, then the causation runs in that direction rather than in the opposite direction. One way of thinking about this and to connect it with what I said earlier about informational independence, you can think of the probability distribution of x not providing any information about the conditional probability of y on x if the correct causal direction is from x to y, since the conditional probability is constant for different distributions of x. In this sort of case, the probability distribution of y will provide information about the probability of x conditional on y, since the latter conditional probability will change in a regular way as the distribution of y changes. And in fact, it's pretty easy to show that in this two variable setup, if you get independence in one direction, that is PR, the probability distribution of x being independent of the probability distribution of y conditional on x, then you can't get it except in highly trivial cases in the other direction. So this is a kind of simple model that I think illustrates some of the ideas about independence, both relationship independence and variable independence that I was talking about earlier. Okay, conclusion, some morals. I've been trying to suggest to you that the directional features of explanation are not merely a matter of pragmatics, they're structural features that tell us in the Flagpole cases that the correct direction goes from h and theta to s rather than in the other way. A plausible account of explanation should tell us why these structural features matter to the goodness of the resulting explanation. And I think ideas about interventions and invariance accomplishes this. Second observation, this was kind of particularly focused on Hempel and the kind of things he had to say about in defense of the DN model of explanation. it's pretty clear that there are structural features in explanations and in causal claims that are not well captured by first order logic. So there are symmetries that may be present if we just look at logical or derivational relations. But if we look at various kinds of independence relations, we see asymmetries, and those asymmetries can be clues to causal direction. Thank you very much. That's it.
Thank you, Jim, for this great lecture. So let me remind you how we're going to be proceeding. If you have a question, just click on the Q&A button at the bottom of your screen and just write your name. I will then move you from the status of attendee to the status of panelist. It might take 1 or 2 seconds for that to happen. No need to write your question, and I will already start moving you right now. John, the floor is yours. John, and yeah.
Can you hear me?
Yes.
Oh, excellent. Jim, thanks very much. That was just terrific. Completely convincing. I just want to check that I've really got it. I want to see how this works in what's an easy, obvious counterexample to the flagpole case, right? Van Frassen has a version of this, but this is the one that I like. So on Monday, we hire an artisan to build a nice flagpole for us in our garden. And we notice that the height of the flagpole does explain the height of the shadow. On Tuesday, we ask the same artisan to build us a sundial, right? And when the sundial's finished, we come out and we're looking at the, you know, the gnomon. That's the little gadget, that the little stick that sticks up, and it's on a funny angle and has a certain length. Now, you know the way that the sundials are built. You design the gnomon in order to give you a shadow that goes on the plate of the sundial that will then read the time well. So the artisan is going to construct the gnomon in such a way that you know, that the shadow will fall where it's wanted. So very briefly, then you would say the shadow explains the height and orientation of the gnomon. Now, I take it, I'm now trying to be you and just talk through the case, so tell me if I'm getting this right or wrong. I take it the way it works is that there are different causal processes at work here. Right? Both of them are artisans doing things, but the causal process in this case is of an artisan who is competent at building sundials, and in an invariant way will always produce a sundial that has the correct relationship between the shadow and the height of the gnomon, because that's what it is to be competent. And then I'm assuming that if we apply all of your conditions to that process, we're going to find in this other circumstance that the height of the shadow will explain the height of the gnomon. I mean, if I've got it, then you'll say that's right. If I haven't, then you'll correct me.
Yeah, no, I think that's basically right. I would think about the case that you describe as the case in which the cause variable is something like the intention of the artisan to produce a device in which there's I guess a height of a certain, well, shadow that of a certain length, depending upon the time of day. So I see the causal variables involved as a little bit different.
Well, let me just say.
So you aren't really, I don't think you're really explaining the height in terms of the shadow. What you're doing is something more like explaining the choice of height in terms of the intentions of the artisan to create a structure in which there's a certain systematic relationship between, you know, the length of the shadow and the height of the sun and the sky, or something like that.
Yeah, that's probably right, and I was anticipating something like that. So that's why I had this story about an artisan on Monday and Tuesday, because the artisan on Monday certainly has an intention to produce a flagpole of a particular height. And I was thinking that maybe that'll make the two accounts that are going to be given more symmetric than it would otherwise seem. But I'm not sure that's right, and I think that's what you're telling me.
Yeah, that's what I think. But let me make another remark about this, though, that I think is relevant. So one of the things I emphasized was there's this general thought that, at least in a lot of cases, we don't like it if something like the governing generalizations and the distribution of initial conditions are too closely tuned to one another. But there are, I think, an important class of counterexamples to that. And these are various biological systems that are subject to natural selection, where it might very well be that the way in which, say, the processing in some sensory system works is very closely tuned because of the operation of natural selection to, something like actual distribution of initial conditions that an organism finds in its environment. So I think these anti-tuning intuitions that I've been appealing to, they have to be treated with care. There are cases in which they can fail, because if you, to the extent that you have things that are designed even by either by natural selection or perhaps also by artisans, the intuitions can be mistaken.
Okay, thank you.
Thank you very much, John. Porter, the floor is yours. Just don't forget to mute yourself.
Hey, Jim, can you hear me?
Yes, I can, Porter. How are you?
I'm all right. So I want to pick up on sort of the tuning intuitions that you just mentioned, talking to John.
Yeah.
I mean, the broadest question I have is kind of vague. I mean, causal faithfulness as a restriction is often kind of treated as another anti-fine-tuning condition.
Right.
Do you know, I mean, do you have a clear picture of how exactly the algorithmic independence conditions relate to the cases that would also be ruled out by a causal faithfulness restriction?
That's a very good question, and I don't know the answer to that question. The conditions seem to be at least somewhat different from one another, and the kind of independence reasoning among facts about causes or initial conditions that I appealed to in handling the Flagpole case actually seem to be weaker than the kinds of assumptions that go into faithfulness. The way in which, so if you had so you can also get inferences about causal direction out of the faithfulness condition as well as what I was talking about. In the case of the Flagpole, what I basically did was to restrict the space of possible hypotheses very strongly. So there were really only two alternative hypotheses I was considering, either S and either H and theta cause S, or S and theta cause H. And if you restrict things in that way, then it seems to me you don't need faithfulness. If you were just looking at an arbitrary structure involving three different variables, and you didn't restrict the space of possible hypotheses at all, then you would need something like faithfulness to get the correct causal direction in the general case. But your question about the relationship between what I call relationship independence and faithfulness is a very good one, and it isn't one that I have thought about. Interestingly enough, the faithfulness condition also fails or can fail in situations where you have natural selection or designed artifacts present.
Yeah. Yeah. I mean, that's your mention of the biological case also kind of brought this question to mind for me. Yeah. Thanks.
All right. Thank you. Well, good to see you. Siddharth, the floor is yours.
Thanks. Hi, Jim. So there's a line of argument that there's a certain, some physicists I've heard, especially in the more sort of quantum information community, make, and the clearest expression of this has been this physicist at the Perimeter Institute called Robert Speckins. And he has argued that, look, what we should really look for when we're thinking about what physical theories are is just the kind of statistical predictions and the correlations between different observations that they do. And we can formulate physical theories in different ways, which will, if we sort of translate it into a causal graph structure, we'll have sort of different kinds of causal graphs. So you can imagine something like Hamiltonian and Newtonian mechanics, where in Hamiltonian mechanics, the causal relations are between positions and momentums at one time to the positions and momentums at the other time, and so on, versus in Newtonian mechanics, it's just positions causing future positions all the way through. So, and he's saying like these are equivalent because they make the same kind of predictions for the whatever observable things you can make, or more precisely, whenever you're looking at sort of statistical dependencies, you can sort of have the same kind of statistical correlations for both kind of causal structures. So they're kind of equivalent in this way. So my question is something like, from based on what you said, it seems to me that you might still sort of think that, you know, when you look at these kinds of statistical correlations, you might still want to sort of prefer certain causal structures over others, even if in some sense they present the same kinds of correlations. Do you think that this kind of framework will let us make a clearer distinction between what is the state space of a theory and what is the dynamical laws of that theory? Or yeah, that's the question.
Yeah, well, thanks. I'm not sure that I entirely understand your question because I don't know the Speckins' work. I know that he and a bunch of other physicists are using causal modeling methods to try to understand what's going on in quantum mechanical and other kinds of cases. But let me try to respond anyway. So if you the kinds of causal modeling work that has been done by Pearl and the people at CMU makes use of statistical information that just has to do with independence, dependence, conditional independence, conditional dependence. So that's the only information that those discovery algorithms make use of in trying to engage in causal inference. It's well known, in fact, there are theorems, that if that's the only information that you have, you face underdetermination problems in the sense that you can have graphs that are different in structure, but have exactly the same implications for the independence and dependence relations you'll see, even assuming faithfulness in addition to the Markov condition. So there's an underdetermination problem there. Now, what this machine learning work does is that it looks at other features of the distributions, and it also makes assumptions about what the functional forms are. And that means you can get around at least some of the underdetermination problems. So what looks like underdetermination in the Pearl CMU framework isn't necessarily underdetermination if you have, if you focus on the kind of additional information that these machine learning algorithms make use of, and if you also make some kinds of assumptions about functional form. So in the Perl CMU framework, if all you have are two correlated variables, X and Y, there's nothing about that information by itself that's going to tell you. They can't answer the question of whether X causes Y or Y causes X. The machine learning guys say, well, in some cases, depending upon what the distributions look like and depending upon whether certain additional assumptions are satisfied, then you can answer that question. Yeah, so if the claim of Speckens and others is that there's this generic underdetermination problem, I think it may well be, and it would really depend on the details of the case, that you could perhaps get around at least some aspects of the underdetermination problem by making use of this, the kinds of additional information that is exploited in these machine learning techniques.
Yeah, thank you. That answered the question perfectly. Thanks.
Thanks, Silas. We have time for a last question. If anyone wants to put his or her name in the Q&A box. No taker? No takers then. Since we're reaching anyway the end of our meeting, I wanted to thank you, Jim, for this talk, and hope to see all of you on next week for the Lunchtime Talk, the annual lecture series, and as a cognitive ontology seminar. Thank you, Jim, for the lecture.
Thank you very much. I apologize. I think my delivery was a little disjointed. It's 9 in the morning here, and I'm usually not functional at this time of day.
Well, it was very clear, despite the issues with the time and also the issues at the beginning, to connect you. So thanks for the lecture.
Thanks to all of you for your questions, and great to see all of you.
Bye, Jim. See you soon.
Yeah, bye.